Okay, so in today's class, we are going to be discussing possibility diagrams. Now, possibility diagram is a diagram that makes it easier to list all the possible outcomes without missing any out or repeating any outcomes. So it's used when you have several outcomes, okay? In an event when you have several outcomes, it's difficult to list them down systematically. So in order to counter that, we draw a possibility diagram so that we have all the possible options in front of us and we don't miss out any of the outcome. Now remember that possibility diagrams are drawn for two events taking place at the same time. Okay. So the question says, two fair six-sided dice are rolled and the scores are added. Two fair six-sided dice are rolled and the scores are added. Draw the possibility diagram to show all the possible outcomes. We are dealing with two dice. Each die will have an outcome of from 1 to 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Let's say this is the first die. And this is the second dice. Now we are calculating the scores. The scores is calculated by adding the two numbers. Okay, and the scores are added. So when you have one on the first die and one on the second die, the score is going to be 2. When you have one on the first die and second on the second dice, the score is going to be 3. When you have one on the first dice and 3 on the second die, the score is going to be 4. Similarly, 5, 6, and 7. Right? Is this thing clear to everyone? Similarly, you're going to be adding for every row. So 2 added with 1. If you have 2 on the first die and 1 on the second die, your score is going to be 3. If you have 2 on the first die and 2 on the second die, your score is going to be 4. If you have 2 on the first and 3 on the second, your score is going to be 5. Okay. Similarly, you're going to add them up. So you can fill in this possibility diagram. Is the possibility diagram clear to everyone? Okay, I have written all the total scores with red color. Now, this is the possibility diagram. Possibility diagram is only going to be drawn for 2 trials taking place. Okay. It has a limitation that it is used for only 2 trials. Now, the second part says, work out the probability of getting a total score of 12. How many total options are these? 1 and 1 is going to give you a score. 1 and 2 is going to give you a score. 1 and 3 is going to give you a score. So if you count all these possibilities, okay, there are 36 possibilities, right? So what is the probability that out of these 36 possibilities, your score is going to be 12?
1
out of 36. So B part 1, the probability of getting a score of 12 is 1 out of 36. Okay, part 2 says getting a total score of 8 or more. Getting a total score of 8 or more. So you're going to count from the possibility diagram. How many times are you getting a total score of 8 or more?
15 over 36.
4, 5, 6, 7, 8, 9. So the score could be 8, 9, 10, 11, or 12. So you count the possibilities. probability of having a score of 8 or more is going to be 15 out of 36. You can simplify this, and the probability is going to be 5 upon 12. Okay. Part C says, what is the most likely total score? The most likely total score is going to be the one with the highest frequency of occurrence. So which score is repeating itself the most?
7.
7. Okay. So the most frequent score or the most likely total score, because 7 occurs most of the time, so the probability of 7 is going to be the maximum. Okay. Probability of 2 is 1 out of 36. Probability of 2 is 3 is 2 out of 36. Probability of 4 is 3 out of 36. Probability of 5 is 4 out of 36. Probability that the score is 6 is 5 out of 36. And probability that the score is 7 is 6 out of 36. And then the probability of 8 is again less, 5 out of 36. So the most likely score is 7. Any questions still here? Okay. The probability of 7 is the highest. The probability of 7 is 6 out of 36. That is 1 out of 6. Any query in this question? All clear?
Yes.
Okay. Now let's try this question. A fair coin is flipped and an unbiased 6-sided dice is rolled. So you have two different trials, a fair coin and an unbiased dice. Unbiased 6-sided dice. Draw a possibility diagram to show all the outcomes. So 1, 2, 3, 4, 5, 6 for the dice, and the outcomes of the coin are going to be head or a tail. So you can have head on the coin and 1 on the dice, head with a 2 score, head with a 3, head with a 4, head with a 5, head with a 6, tail with 1, tail with 2, tail with 3, tail with 4, tail with 5, and tail with 6. These are all the possible outcomes. Correct?
Yes.
Now it says work out the probability of getting a tail and an even number. What is the probability of getting a tail and an even?
6.
Getting a tail and an even number. So with a tail, you need to have 2,
Oh,
4,
3.
and 6. 3 out of
3 out of
3 out of how many options?
12.
12. So probability of getting a tail and even number is 3 out of 12. That is 1 out of 4. Okay. Understood?
Yes.
Zarva, any questions still here?
No.
Okay. The next thing that we are going to do is tree diagram. It's another way of showing the possible outcomes of combined events. Okay. So we are doing combined events right now, like flipping a coin and dice together. The two events are combined together. So one of the ways of showing the possible outcome was a possibility diagram. The other option is the tree diagram. Okay. So tree diagrams are particularly useful if each event has several possible outcomes and there are more than two events to be combined. The limitation of the possibility diagram was that it was drawn only for two combined events. If you have more than two events combined, then obviously you're going to draw a tree diagram. So let's try to understand how does a tree diagram work. So the first event is flipping a coin, flipping the first coin. So over here you have two fair coins. You are flipping the first coin and then you're flipping the next coin. If you flip the first coin, there are two options. You can get a head or you can get a tail. Okay, these are called the branches. The probability of getting a head is 1 upon 2. The probability of getting a tail is 1 upon 2. Now, when you flip the second coin, let's say you flip the first coin, you get a head, and then you flip the second coin, you are going to have two options. Either you are going to get a head or a tail, right? The probability of getting a head, since it's a fair coin, the probability of getting a head is going to be 1 upon 2. The probability of getting a tail is going to be 1 upon 2. Now, if your first coin was a tail, then when you are going to flip the second coin, you could have head or a tail. The probability of getting again a head is going to be 1 upon 2 and the tail is going to be 1 upon 2. So these are the possible options. Either you can get a head on the first and head on the second, head, or you can have a head on the first and tail on the second, that's head tail, or you can have a tail on the first and tail on the second, sorry, tail on the first and head on the second, or you can have tail on the first and tail on the second. These are the only possible options. Okay, so if you are asked to calculate the probability of getting both heads, so what you are going to do is you're going to multiply the probabilities across the branch. 1 upon 2 times 1 upon 2. So probability of getting a 2 head is 1 upon 2 times 1 upon 2, that is 1 upon 4. If you're asked to get a probability of 1 head and 1 tail, so either your first coin get a head and the second coin get a tail, or you can get a first tail and a second head. So you're going to evaluate the probabilities of both. So either it can be probability of head tail or probability of tail head. The probability of head tail is again 1 upon 2 times 1 upon 2, that is 1 upon 4. The probability of getting a tail and a head is 1 upon 2 times 1 upon 2, that is also 1 upon 4. So 1 upon 2 plus 1 upon 4 plus 1 upon 4 is 1 upon 2. Okay, then if you are asked to find the probability of getting both tails, that's going to be 1 upon 2 times 1 upon 2, that's 1 upon 4. So if you add all the probabilities, they must add up to 1, right? So 1 upon 4 plus 1 upon 2 plus 1 upon 4, that adds up to 1. Is the tree diagram clear? Is this tree diagram clear?
Yes.
Okay, let's try this one. A bag contains 5 red counters and 3 blue counters. Jasmine picks a counter at random from the bag and notes its colors. She puts the counter back in the bag. Jasmine then selects a second counter and notes its color. Find the probability that both the counters are red. So the best way to go about this question is to draw the tree diagram. There are 2 picks. Okay, there's a first pick. In the first pick, she can either get a red counter or a blue counter. If the first pick was a red counter, then in the second attempt, she can get a red counter or a blue counter. If the first pick was the blue, then she can get the red in the second or the blue in the second. So that's your tree diagram. You are going to write down the probabilities. What is the probability of getting a red counter in the first attempt?
1/2.
See, there were 5 red counters.
Yes.
So 5 upon 8. Okay. Does everyone agree that the probability is going to be 5 upon 8?
Yes.
So 5 out of 8, that's the probability of getting a red counter. What is the probability of getting a blue counter?
3/8.
3 over 8. And you must notice that every time, so this first option has 2 outcomes. If you're going to add the 2 probabilities, it will always be equal to 1. So if we know this as 5 upon 8, we can calculate this by 1 minus 5 upon 8, that is going to be 3 upon 8. Now, the most important line in this question is, she puts the counter back in the bag. So when she puts the counter back in the bag, the total number of counters again in the bag are the same. So after she has put, let's say she picked up the red color and she put it back. Now in the bag, how many counters are there in total? How many counters are there in the bag? She just,
8.
yes, 8. She just notices down the color and she puts it back. And the probability of, and there are 5 red counters. So the probability is going to be 5 upon 8. Similarly, this is going to be 3 upon 8, 5 upon 8, and 3 upon 8. Okay, now you have been asked to find the probability that both the counters are red and red. So the probability of getting a red and a red counter will be this branch. So you're going to multiply the probability of getting a red counter in the first attempt times the probability of getting the second red counter. So that's going to be 25 upon 64. Okay. What is the probability of getting both the blue counters? What is the probability of getting both the blue counters?
9 over 64.
So 3 upon 8 times 3 upon 8, that is 9 upon 64. What is the probability that one counter is red, one is red, and the other is blue? What is the probability that one is red and the other is blue?
15 over 64.
So you are the possible options are that you can have red and blue, or you can have blue and red. Okay, so there are two options. Probability that the first one is red and the next one is blue, or if the first one is blue and the next one is the red. So you're going to add the probabilities over here. 5 upon 8 times 3 upon 8 plus 3 upon 8 times 5 upon 8. So when you add this up, you get 30 upon 64. Is that correct, Zarva?
Yes.
Okay. Any questions still here? Zona, any questions still here?
No, sir.
Okay. Guys, try this one. A fair 6-sided dice is rolled twice. Find the probability of not getting a 6. I want everyone to try this question.
5 over 6.
A fair 6-sided dice is rolled twice. You need to find the probability of not getting a 6. So let's say if you roll the dice and you can consider two options. Either you get a 6 or you don't get a 6. If you get a 6, then on the second dice, you either get a 6 or you don't get a 6. If you don't get a 6 on the first attempt, then on the second attempt, you either get a 6 or you don't get a 6. That's the tree diagram. Okay. Omar, what is the probability of getting a 6 on the first dice?
1 over 6.
1 upon 6. And what is the probability of not getting a 6?
5 over 6.
Okay. Will the probability be the same in every case?
No.
Like will the probability of getting a 6 or not getting a 6 will be the same as the first dice? Yeah, because
No.
these are independent events. The probability of getting a 6 on the second dice is not affected by the probability of getting a 6 on the first dice. Okay, the probability will remain the same, that is 1 upon 6. Are you getting my point?
Yes.
The probability of getting a 6 on the second die is not affected by probability of not getting a 6 on the first die. It's going to remain the same, 5 upon 6 and 1 upon 6 and 5 upon 6. Now the question says find the probability of not getting a 6. Probability that you do not get a 6 on two throws. So not getting a 6 and not getting a 6. So that is simply this branch, not getting a 6 and not getting a 6. So 5 upon 6 times 5 upon 6, that is 25 upon 36. Clear? If you're done with this, please try the next one. So a fair coin is flipped 3 times. If the coin is fair, then the probability of every outcome, the probability of getting a head and a tail is the same. Okay, that is 1 upon 2. Now, a fair coin is flipped 3 times. That means that you're going to get a head or a tail in the first attempt. Okay, either you're going to get a head or a tail. If you get a head in the first attempt, then you have 2 options. You're going to get head or a tail in the second attempt. And in the third attempt, again, you are going to have head or a tail. Head or a tail. If you get tail in the first attempt, then you can have head or tail in the second. Head or tail. Head or tail. Would you agree that this is going to be our tree diagram? The respective probabilities are going to be 0.5, 0.5, or you can write 1 upon 2 as well. Okay. 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5, and 0.5. Now, they want the probability of getting one or more tail. Which branches are going to be involved in one or more tail? Which branches are going to be involved in getting one or more tail?
All the branches which has tails.
All the branches that have tail. So head, head, tail, head, tail, head. One or more means at least one tail should be there. There could be more than one tail. Tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. So except for only one, this branch, every other branch is included. Okay, so you can find the probability of this branch 0.5 into 0.5 into 0.5 plus 0.5 into 0.5 into 0.5 plus 0.5 into 0.5 into 0.5. But this is going to be a tedious process. The alternate way of solving this is you find the probability of getting a head, head, and a head, all 3 heads. So if you want the probability of at least one tail, then you can minus the probability of all the heads from 1. What is the probability of getting all heads? All heads means head, head, and head. That is 0.5 into 0.5 into 0.5, right? So 1 upon 2 into 1 upon 2 into 1 upon 2 is 1 upon 8. So the probability of getting at least one tail is going to be 1 minus 1 upon 8, that is 7 upon 8. Is this thing clear? Is everyone clear with the working? Omar,
Yes.
Abdul Rahim, Zona, Zarwa?
Yes.
Okay. Okay, now we have already done sets. The probability questions are also tested with the concept of sets. So we are going to be looking at probabilities using Venn diagram now. A group of 40 students. Okay, I want you to try this first on your own. I'll just pause the recording and you can try this on your own first. I want you to draw a Venn diagram first, and then we are going to be answering this together. Okay, so a group of 40 students at a performing arts school were asked whether they learned ballet or tap dancing. 24 said they learned ballet, and 9 said they learned tap dancing only. 11 said they learned both ballet and tap dancing. Show this information on a Venn diagram. So you're going to have two sets. One is ballet and the other one is the tap dancing. 11 said they learned both. So that's the common value. Intersection, that's going to be in the intersection. 20 in total, 24 learned ballet dancing. So 24 minus 11 is going to give you 13. Okay, 9 said they learned tap dancing only. So that's where 9 comes in. So the class was of 40 students. You have accounted for 13 plus 11 plus 9. Okay, that's 33 students. So how many of the students are going to be over here?
7.
7. That's your Venn diagram. Now, if a student at the performing arts school is chosen at random, what is the probability that they only study ballet? So how many students study ballet dancing? Only study ballet, okay? Probability that only ballet dancing is selected.
13 over 40.
13 upon 40. Good. What is the probability that they do not study either ballet or tap dancing?
7 over 40.
7 over 40. All right. Good. Okay. Now, the next topic that we are going to discuss is the conditional probability. This is mostly tested in the extended exams. With conditional probability, the likelihood of an event depends on other events that are related to it. So we are going to be talking about the dependent events. In the previous section, we have seen independent events. Now we are going to be discussing dependent events. For example, the probability that you will get sunburn depends on various factors. It depends on the length of the time you go outside in the sunshine. Okay. So you getting a sunburn depends on the length of the time you are outside your house. It depends on the time of the day as well, because we know that right in the afternoon when the sun is right above you, that's when you feel extremely hot. Or whether the temperature of that city is high enough, then you are going to get sunburned. Okay. So these are the factors that determine whether you are going to get a sunburn or not. So the two events are the time, the duration, and the sunburn. So these are dependent events. Take another example. A car insurance company will calculate the premiums it charges its customer based on the likelihood of a driver having an accident. Okay. So you're going to be charged more if you are a driver with having less number of skills of driving. Okay. If you do not know how to drive properly, or let's say you are at a young age, you don't have any much experience for the driving, your premium, your car insurance company might charge you a premium amount. So the amount that you are going to be charged depends on your experience, driving experience. Okay. Or the number of accidents you have. For example, two people go for the insurance, and one has got 5 accidents in the past 2 years, and the other one has a zero record of accident. So this means that the person with a zero record of accidents will be giving less premium, and the one with a higher number of accidents will be giving more premium amount. Data about gender, age, and how far a person drives, that's also taken into account. So the premium that needs to be calculated, the premium amount that it's going to be calculated depends on many factors. So these scenarios are basically dependent events. Okay, let's discuss this example. Sorry. Rakesh either walks to work or catches a bus. The probability that Rakesh will walk is 0.7. Okay. So there are two options. Either he walks to work or catches a bus. So I'm going to be drawing a tree diagram to simplify the working. Either he walks or he get a bus. The probability that Rakesh will walk is 0.7, and the probability, okay, now that then the question says, if Rakesh walks, the probability that he is going to be late for the work. So the other event is that he's either going to be late or he's not going to be late. If he goes by bus, there is a probability that he's either going to be late or he's not going to be late. If you are able to draw the tree diagram, the question is going to be very much simplified. Then the question says the probability that Rakesh will walk is 0.7. So what is the probability that he goes by bus?
0.3.
0.3. So 1 minus 0.7, that is 0.3. Now the question says, if Rakesh walks, the probability that he is late for work is 0.4. So there is a 40% chance that he is going to be late for sure. Okay. What is the probability that he is not going to be late?
0.6.
0.6. Then the question says, if he catches the bus, the probability that he is late is 0.45. If he catches the bus, then the probability that he is late is 0.45. So what is the probability that he is not late?
55%.
55%, that is 0.55. Okay. Now, can I say that that getting late and walking are dependent events? Because the probability of getting late is not the same. Okay, it is getting affected by either you are walking or you're taking a bus. Okay, do you see that?
Yes.
Okay. Now, one might think, why is that the case, that although he's taking a bus and he's getting late, that maybe because when he walks, he takes less number of time to reach the office. Okay, and the bus, when he takes the bus option, the traffic is so much that he is usually late. So that is why that could be a reason that catching a bus will mean that he is going to have a higher chance of getting late. Okay, while instead of walking. Okay, so we need to calculate the probability that Rakesh gets to work on time. Getting works on time means that he is not getting late. So you need to find the probability that he is on time. On time means that he is not late. Okay, so he is not late when he walks and he is not late, or he takes bus and he is not late. So what is the probability going to be? 0.7 times 0.6, okay, plus 0.3 times 0.55. So what's the answer? What's the final answer, guys? What is the probability that he gets on time? Just add this up. Zarwa, what value are you getting?
0.585.
0.585. Good. Okay. The second part says the probability that Rakesh is late for work. Probability he is late. So he can be late either by choosing to walk or by taking a bus. So 0.7 times 0.4 plus 0.3 times 0.45. Okay. So that's going to be 0.415. The alternate way you can do is probability of getting late is equal to 1 minus probability of not getting late. The probability of not getting late was 0.8585. So 1 minus 0.585 is going to be 0.415. That's also one way to go about this question. Yeah? Zona, is the word
Yes.
clear? Okay. Let's try the next one. A bag of sweet contains 10 cherry flavors and 8 strawberry flavors. Maria takes 2 sweets at random from the bag and eats them. Work out the probability that both sweets are cherry flavor. Now, this is the question where the events are where the events are dependent. Okay. You need to work out the probability that both sweets are cherry flavor. How would you do that?
We are going to make a tree diagram.
You're going to make a tree diagram. Okay. So either it's going to be a cherry flavor or a strawberry flavor. The first, let's say she picked up the first sweet and it's a cherry flavor. So what's the probability of picking up a cherry flavor?
0.5.
10 out of 18. There are 10
Oh,
cherry
yes.
flavor and 8 strawberry flavor. And strawberry flavor probably is going to be 8 out of 18. Then what she does is she eats one of that, okay, and she picks up another. The next one could be a cherry flavor or a strawberry flavor. So now what is the probability of getting a cherry flavor? If she has not kept the first sweet back in the bag, so how many sweets are there in the bag now? How many sweets are there now in the bag?
17.
17. Good. And out of these 17, one cherry has been taken. So how many are going to be left? Out of 10, one cherry is gone. So
9.
9 are going to be left. And out of 17 in the bag, there are going to be 8 strawberry flavor sweets. Similarly, the second branch is going to be 10 out of 17, right? And 7 out of 17. Please remember that adding these two will always give 1. Adding these two must give 1. Okay. Now, you have drawn the tree diagram. Work out the probability that both sweets are cherry flavor. Both sweets are cherry. Cherry and cherry. So what's the probability going to be? Cherry and cherry means this branch. Okay. So 10 upon 18 times 9 upon 17. What's the value?
5 over 17.
5 upon 17. Part B. Find the probability that one sweet is cherry and the other is strawberry. One sweet is cherry and the other is strawberry, or you can have the first one strawberry and the second one cherry. So these are the two branches you are going to add the probabilities. So 10 upon 18 multiplied by 8 upon 17 plus 8 upon 18 times 10 upon 17. Add them. What's the answer?
4 upon 9.
No. I'm getting 80 upon 153.
So sorry, I accidentally added both strawberries.
Okay. So that's the answer. Zarva, is the answer correct? Abdul Rahim?
Yes.
Now we want both sweets to be strawberry. So that's going to be strawberry and strawberry. So 8 upon 18 times 7 upon 17. That's going to be 56 upon. Okay, if you simplify this, you should get 28 upon 153. Are we getting the right values?
Yes.
Okay. Let's try this one. A bag of counters contain 5 green counters and 4 red counters. Majid takes 3 counters at random from the bag without replacement. That means every time the probability is going to be changing. Okay. So in the first trial, you can have either a green counter or a red counter. In the second trial, either a green or a red. In the third trial, either a green or a red. Green or a red. That's the tree diagram. The probability that the first counter is a green counter should be 5 upon 9, and the probability that the first counter is a red counter should be 4 upon 9. If the first counter is a red counter, then the probability that the next counter is going to be a green is going to be 4 upon 8. That's correct?
So why is that?
Because it's without replacement. You have taken the counter outside now. Now, to get the second counter as a green counter, you will have to choose. So out of 8 counters in the bag now, there are 4 green counters. So the probability is going to be 4 upon 8. Okay. And out of 8 counters in the bag, there are 4 red counters. Are you clear with this?
Yes.
Okay. What's going to be the probability that the third counter is going to be a green counter? What's going
3
to be
over 7.
3 upon 7? Good. And this is going to be 4 upon 7. Okay.
So why 4 upon 7?
Because 1 minus 3 upon 7 is 4 upon 7. Or you could understand it like this as well. So 2 green counters have been taken out. So out of 9, now there are 7 counters in the bag, out of which 4 are red counters.
So
Okay.
how do you know that we have taken a green counter, not a red counter?
So green, green, and green, and green, green, and a red. So I'm doing this branch right now.
Oh yes, sorry.
Okay. Now the next is green, red, green. So out of 7, how many green counters are going to be there?
5.
So there were initially 5 green counters. 1 green counter has been taken. 1 red counters have been taken. So now the remaining green counters should be 4. Okay. And this is going to be 3 upon 7. Okay. Now let's try this one. If the first counter was a red, then the second counter is a green. What's the probability that the second counter is a green? It's going to be 5 upon 8. 1 minus 5 upon 8 is going to be 3 upon 8. Now, if the first was a red and the second was a green, then the third counter is green. What's the probability that the third counter is going to be the green? There are going to be 7 counters in the bag. 1 green has already been taken out, so it's going to be 4 upon 7. So the next one, the probability of getting a red counter in the third trial is going to be 3 out of 7. Okay. If both the red counters have been taken out, now there are 5 green counters in the bag out of 7, and that's going to be 2 upon 7. Clear? Now you need to work out the probability that all the counters are of the same color. Now the same color means that either the counters are green and green or red, red and red. So probability that the counters are of the same color means either they can be green, green and green, or they can be red, red and red. The probability of green, green, green is 5 upon 9 times 4 upon 8 times 3 upon 7. And the probability of getting a red, red and red is 4 upon 9 times 3 upon 8 times 2 upon 7. Okay. So the probability of green, green, green comes out to be 5 upon 42. And the probability of red, red and red comes out to be 2 upon 42. So when you add them, you get 7 upon 42, that is 1 upon 6. Is this clear to everyone?
Yes.
Sure. Any questions?
Yes.
Okay.